Hi everyone, this week we are going to go over risk, as in life is uncertain, life is risky, and how do we measure utility and how do we make decisions in economics under risk. First, the usual disclaimer. I do not allow this content to be published without my consent. If I see this content published online, I will take it down and report whoever posted it. So the outline for today is going to be first to talk about expected utility. I will talk about expected utility in the case of risky outcomes and how individuals are going to make decisions over risky, gambles or lotteries. Then I will talk about risk aversion in particular. I will talk about what it means to be risk averse, how it is measured, and how we compare two people which are risk averse. Finally, I will apply the concept of expected utility and risk aversion to the case of insurance. Life is uncertain, and it is one of the reasons we pay for insurance. First, let's start with expected utility. So one distinction I want to make first is that in economics, or in more fields in general, we distinguish risk and uncertainty. We talk about uncertainty when the probabilities of events occurring are unknown, and risk when they are known. So you will often hear people say life is uncertain, life is risky, but there is a slight distinction to make. Life is uncertain when you don't know with what probability things can happen, but life is risky when you know the associated probabilities to each event. For instance, if you go to the casino and you play poker, you will face a risky gamble in the sense that you know the probabilities of you winning a hand given what the other ones can have. Uncertainty would be more related to the probability of getting into a car accident. You could maybe estimate this number, but in general, you never know. You could be crossing the street and boom, a car runs into you. So how do people evaluate choices that yield risky outcomes? Things such as a lottery or a gamble. I'm going to give you an example. Think about the lottery that I'm going to call L, that pays either an amount x1, which is equal to $100 with a probability p, or $200 with a probability 1 minus p. So it's either $100 or $200 of gains. The lottery can be written then 100p semicolon 200 1 minus p. The way to read it is gain of 100 with a probability p, gain of 200 with a probability 1 minus p. Now, if you think about a scratch game, you know those tickets that you buy for $1 that you scratch? There are probabilities associated to each gain. Imagine that this lottery is a scratch game. You can either win $100 or $200. The expected monetary value is the same as the average value of the lottery, the average gain. So with probability P, you make $100. With probability 1 minus P, you will be making $200. This is the expected gain, so expectation of L, which is why you have this bold E. Now, is it really what we care about when we decide whether or not to pay for such a lottery ticket? Do we care about the average gain, or rather, do we care about the utility we have over the gains? The expected value doesn't tell you how much utility you're going to get from the gamble. So the actual relevant concept to use is going to be not the expected value, but the expected utility of the lottery. You can see the difference here. From expectation of L, we went to expectation of U of L. expected utility of the lottery. So with probability P, you will make a gain of 100, but your utility is not equal to 100. Your utility will be equal to U of 100. With probability 1 minus P, it will be equal to U of 200. Depending on the shape of the utility function, this number will be different. And in general, it will not be the same as the expected gain. So more generally, consider a lottery L which has uncertain outcomes that go from x1 to xn. So there are n possible cases. When you scratch, when you play a scratch game, you could win $1, $2, $5, $10, $1,000, and maybe $1 million. There are multiple outcomes. Each of them occur with probabilities P1 all the way to Pn. To each gain is associated a probability. The expected utility function, which is also called the von Neumann-Morgenstern utility, it is related to the creators of this concept in the 1944-45. This function assigns a utility value, u of xi, to each possible outcome. So, the utility value of the lottery, because it is not played yet, will be the average value of u, or the expected value of the utility. With probability P1, your utility will be u of x1. With probability P2, your utility will be u of x2, and so on and so forth. The same way you compute your average grade, or your average gain, or your average wage, and so on, you can compute your average utility over something that is risky. Note that if the lottery was uncertain, then we would not be able to do this because we would not know what P1, P2, and so on would be. With risk, we know what they are. You know the exact probability of making each gain, and you can compute your expected utility accordingly. Remember, u of x, the utility function, is cardinal. It assigns a number to a lottery or to an outcome in general. So it is not ordinal. An ordinal relationship is a ranking between two different options. For instance, I could say, I prefer tea to coffee. This is ordinal. I am ranking tea first and coffee second. If I put a utility function on my pleasure derived from tea and coffee, maybe my utility from tea could be equal to 10, and the utility of drinking coffee could be equal to 1 or 2, because I don't really like coffee too much. Whether it's 10 versus 2 or 100 versus 20 or 1,000 versus 10 doesn't really matter. What matters is that tea gives me a higher utility than coffee. Note that a negative utility is not important. It is not important. What matters is how high a utility is compared to another. If the utility of drinking tea is equal to -1 and the utility of drinking coffee is equal to -2, then it doesn't matter. My utility from drinking tea is higher than my utility from drinking coffee. So don't really worry about the sign. Now, the shape of the utility function, so whether it's a Cobb-Douglas, quasi-linear, linear, and so on, will determine the attitude towards risk. It will tell you how likely a person is to accept or reject a gamble. So, the same way I talked about preference between tea and coffee, like I prefer tea to coffee, we are going to define preferences over a lottery. An individual prefers lottery L to another lottery L prime, which has other gains and other probabilities. And in this case, we write L preferred to L prime, this symbol is not a symbol of being bigger, it's a symbol of being preferred. So it's a wavy bigger than equal to sign. This ordinal preferences, I prefer this to that, translates in utility terms to the expected utility from lottery L is bigger or equal to the expected utility derived from lottery L prime. So if I get a higher expected utility from one lottery over another, then I will prefer that lottery. Now note that all of these preferences, all of these expectations happen before we actually play the lottery. Once we play the lottery, it's going to be either one or the other outcome. Either you make $100 or you make $200 or you make any other gain. So expectation happens before you play the lottery. I don't know yet what I'm going to get, but my expected utility is going to be this much. Once you play it, you make your gains and your utility becomes, it's not an expectation anymore, it becomes a non-random quantity. So imagine we have two lotteries. The first one pays 100 with probability 50% and $225 with probability 50%. The second lottery pays $25 with probability 20%, $144 with probability 50%, and $256 with probability 30%. Note that those probabilities sum up to 1 every time. If it's one outcome, if it is not one outcome, it's going to be another outcome. Imagine the utility function is square root of x. That should look familiar. I'm pretty sure you've seen utility functions like that before. I have shown one like this in the public goods lecture and games application lecture. Which lottery is going to be preferred? On one hand, this one only has two outcomes, which are fairly good. This lottery has more outcomes, has 3 instead of 2. One of them is pretty low, but 2 of them are pretty high. So it's not obvious which lottery is going to be preferred. Well, compare the utility, the expected utility with each lottery and see which one is bigger. The expected utility of lottery L will be with probability 0.5 square root of 100, because x is equal to 100 in this case, and with probability 0.5 it's going to be the square root of 225 because x is equal to 225. Now the numbers are pretty nice because the square root of 100 is equal to 10 and the square root of 225 is equal to 15. So it's easy to compute and we get an expected utility of 12.5. In itself, the number 12.5 doesn't mean much. It is mostly meaningful when we compare it to another expected utility. With L prime, we have with probability 20%, we have square root of 25. With probability 50%, square root of 144. And with probability 30%, square root of 256. Again, numbers have been picked so that square roots are nice. Square root of 25 gives you a 5. Square root of 144 gives you a 12. And the square root of 256 gives you a 16. The overall expected utility is going to be 11.8. So, the first lottery that has less outcomes is preferred to the second lottery. Note that if instead of 25 here, I had, let's say, 64, so here we would have 0.2 times not 5 but 8, maybe the expected utility of the second lottery would be higher than the expected utility with the first lottery. Any questions so far? This needs to be understood before I move on. Okay, no questions in the chat, then I'll keep going. So now that we have defined how utility is measured when an outcome is risky, we are going to see how individuals are going to behave when they face risk. So we can compare two lotteries for the same individual, that's what we just did. But how do we compare two individuals regarding their preferences over lotteries? How do we compare my preference and your preference over the same lottery? You could have a utility function of square root of x, and I could have a utility function of log of x, a logarithm, for instance. So we need to characterize preferences over risk. And in order to do this, you can already imagine that one of the main ingredients is going to be the expected utility of a lottery. That's what you can expect to obtain in terms of happiness from playing that lottery. Now, we're going to need another ingredient, which is the average gain obtained for certain. So we're going to distinguish the case where you take the gamble, so you take the risk, and the case where you do not take the gamble, but instead you accept money for sure. The first term has expectation first. So this means this is the expected utility. So you're taking the gamble, and the gamble is risky. The second term is utility first. This means that it is the utility from obtaining this quantity. Expectation of L is the average gain of the lottery. So the red term here is the utility derived from being given the average gain of the lottery. The blue term is the average utility from playing the lottery. So be careful here because the notation are just switched. If you see expectation first, you are saying this is the expected value of what's inside. So you're taking the gamble. If you see U first, this is the utility of what's inside. So the blue term is expectation of the utility. The red term is utility of the expectation. So, a consumer is said to be risk averse if she prefers to receive the expected value of the lottery for sure to playing the lottery itself. In mathematical terms, it means that the red term, the utility of the expected gain, is higher than the expected utility of the lottery. So if I am risk averse, I prefer you to give me the average gain of the lottery for sure, and I don't play the gamble. I just get the lottery. I just get the average gain and I leave. As opposed to actually playing the lottery and taking the risk of getting a small amount or a big amount. That definition is very important. You should know it, of course, by heart. So, let's see how this looks on a graph. Imagine that the utility function is strictly concave. A utility function is concave when the second derivative, u prime prime, is lower than 0 for any value of x. For any value of x. And a concave utility function will have this shape. It's either this shape or it could be a inverted U shape. So you can think of it as the curve, the graph, is oriented towards the bottom, towards the cave. And we are going to oppose that to a convex function. A convex function would be a U-shaped function, for instance. In this case, the function, the graph, is oriented towards the sun, towards the exterior, convex exterior. That's one way to remember it. So let's go back to our previous lottery. $100 or $200, each with equal probability. So the lottery can be written 100.5, 200.5. If I plot the utility function, I can locate the areas, I can locate the points where I make $100 versus $200, which is each possible outcome of the lottery. And then I can look at the associated utility level. That's the utility I would get from making $200. That's the utility I would get from making $100. Okay. Now, how do we compute the expected utility? Well, the expected utility is going to be 1/2 utility of 100 plus 1/2 times utility of 200. So this is an average because we have expectation first. Any average can be taken as the middle point between 2 points. So I have my utility of 100. I have my utility of 200. If I want to find the expected utility, I draw a line between the 2 points, and the expected utility, the point here, will be located according to the different probabilities. Because we are looking at 1/2, 1/2 here, 1/2, then this point is in the exact middle of this segment. But if instead we had 1/3 U of 100 and 2/3 U of 200, then this point will be located around here, or around here maybe, where it's closer to U of 200 than it is to U of 100. Okay? So, right now, we have located the expected utility of the lottery. Note that it is not on the red curve, because on the red curve, it's always U first. Here, we see expectation first. Expectation means we just draw a straight line and find the point in the middle, or somewhere on the segment. Now, if I locate here the average gain of the lottery, which is equal to 150, 1/2 of 100 plus 1/2 of 200 is equal to 150. I can align it with the expected utility here, and I am going to locate the utility of this gain, and this is going to be the red term in my utility function definition. This point here, which is on the red graph, corresponds to the utility of the average gain. Note again, this point is on the graph, and the corresponding number starts with U. So anything on the graph will start with U. If we have a straight line, that's going to be expectation first. And you can see now that the red term, the utility of the expected gain, is higher, vertically speaking, than the blue term, the expected utility of the lottery. This corresponds to the definition of risk aversion. The utility of the average gain is higher than the expected utility of the lottery. So you can already imagine that when the function is concave like that, a straight line leaking 2 points from the curve, the straight line will always be lower than any point on the curve. right? This point is lower than this point. This point is lower than this point. This point is lower than this point. So when the function is concave, strictly concave, then the expected utility will always be lower than the utility of the expected gain. So we see that the red term is bigger than the blue term due to the concavity of the utility function. And that leads us to this very important result. An agent is risk averse if and only if his utility function is concave. So, if you know that the utility function is concave, you already know the agent is risk averse. It's a pretty powerful result. Any questions? This graph and this theorem are very important as well. Okay, no questions? Let's move on. So let's go back to a general lottery that has n different outcomes with the associated probabilities. Then an individual is risk averse if the utility of the expected gain, so utility first and then inside you can write down the expected value of the lottery, if this number is bigger than the expected utility, where now we have the average utility with P1 U of x1, P2 U of x2, and so on until Pn U of xn. And so risk aversion means that U of x is strictly concave, as mentioned in the previous theorem. If somebody is risk averse, it also means that the opposite means that somebody is a risk lover. And in the middle, we have a concept called risk neutrality. An individual is risk neutral if this inequality becomes an equality. If you do not mind between getting the average gain of the lottery for sure or playing the gamble, then you are risk neutral. And this means in particular that the second derivative of the utility function will be equal to 0. That means that the utility function is linear. So if you see a linear utility function, you can think right away, oh, the agent is risk neutral. And finally, an agent is risk averse, risk loving, if the inequality goes the other way. In this case, the agent prefers to play the lottery as opposed to receiving the average gain of the lottery for sure. And that means that if, there's a typo here, if the agent is risk loving, then his utility function is going to be convex. And here we have lower than 0. Here this time is going to be bigger than 0. If you want an example, think about the function x squared. This function is convex. Take the first derivative. The first derivative is going to be 2x. Take the second derivative, which is the derivative of the derivative. So the derivative of 2x is going to be equal to 2. It is positive at all times. So x squared is convex. And that's how you have this U shape. Okay? Now, how do we measure risk aversion? How can we tell if somebody is more risk averse than somebody else? Well, there are two different measures that we're going to go over. The first one is called the measure of absolute risk aversion. it is the degree of risk aversion can be measured by the Arrow-Pratt measure of absolute risk aversion. Arrow and Pratt are two researchers that made this measure back in the 50s, 60s. This measure is meant to not depend on any linear transformation of the utility function. Imagine that your utility function is square root of x, and my utility function is 2 times square root of x. Who is more risk averse? Well, we are equally risk averse. It's not because my utility is multiplied by 2 as opposed to yours that my preferences over a gamble will change. I will rank gambles the exact same way as you. It's just that the utility I will derive is not the same. This is why they came up with this measure, minus the ratio between the second derivative of the utility function over the first derivative of the utility function, which is the marginal utility. Now, since we talk about absolute risk aversion, there is also a relative risk aversion coefficient. This one is very similar to the absolute risk aversion, except that it is multiplied here by x, x being whatever money we are looking at. So the degree of relative risk aversion can be measured by minus u prime prime over u prime times x. So it is pretty much multiplying the absolute risk aversion, rho A, that's a rho, that's the Greek R, and you multiply this rho A by x. Note that these levels depend on x. It depends on what the income level is. A side note about relative risk aversion. Why is that an interesting concept? The relative risk aversion is the elasticity of the marginal utility with respect to money. Forget about the sign. It measures the 1% or the percent change in marginal utility of money when money increases by 1%. If you remember the definition of elasticity, it is the derivative of whatever quantity you look at, u prime, with respect to x, times x over u prime. So, the first term here, the derivative of u prime with respect to x is going to be u prime prime, right? And the second term is x over u prime. So the formula ends up being x times u prime prime over u prime. Except for the minus sign, you can see that we have pretty much the relative risk aversion coefficient. Now, you might be wondering, why the minus? Well, because in general, people are risk averse. It's a general property. Not in every case, but in general, people are risk averse. And so, it means that u prime prime is going to be negative because the utility function in this case is concave. So, since this term is negative, but this term is positive, we put a minus in front so that the overall quantity is going to be positive. So if you're risk averse, this quantity is positive, but if you're risk loving, u prime prime is positive, so this overall number will be negative. And if you're risk neutral, well, u prime prime is equal to 0. So the risk aversion coefficient will be equal to 0 if you are risk neutral. Rho A and rho R depend on x in general, but not always. So let's go through an example. We already saw the square root utility function. And let's compute the absolute and relative risk aversion coefficients. Before we even get there, is square root a concave function or a convex function? Please let me know in the chat. Think about the graph of the square root function and think about where it is oriented. Okay, nobody in the chat? Well, it is a concave utility function. Now, compute the second derivative of the utility function and the first, and take the ratio. So you will have to compute these things by yourself, and the two minuses are going to cancel out. We have some x here with a minus 3/2 with a square root. The final result will be 1/2x. Note that this is positive, so indeed our agent is risk averse, and it depends on x. Now, if you compute the relative risk aversion coefficient, you take this coefficient and multiply it by x. As easy as that. This coefficient, 1/2, means that if you increase your money by 1%, your marginal utility is going to increase by 1/2 of a percent. Sorry, by 0.5%. Remember, the relative risk aversion coefficient is an elasticity. Note that rho A, here, 1/2x, is decreasing with x. The richer you are, the smaller the risk aversion coefficient. So it means that the richer you are, the less risk averse you get. So we say that this utility function exhibits the decreasing absolute risk aversion property. When you gather the first letter of each word, you get DARA. This utility function in particular, the square root function, is a DARA function. Other utility functions could exhibit a constant absolute risk aversion or a increasing absolute risk aversion. Why not? Now, the relative risk aversion coefficient is 1/2. It is constant. It does not depend on x. So in this case, we say this utility function exhibits the constant relative risk aversion property. So now it's not DARA anymore, it's going to be CRRA property. Okay? Not all utility functions have these properties. For instance, you can try u of x is equal to x minus 1/2 of x squared. Because there is a minus in front of the x, we're going to have an inverted u. And you could also try with u of x is equal to minus 1/x. This utility is guaranteed to be negative, but that doesn't matter. As I said, negative values are not important. What matters is the shape. Try this at home. Let me know in office hours what you find, and that will help you a lot for the rest of the course. Now, I want to talk about two concepts which are related together, which are related to how much money are you willing to accept or pay to not play the gamble. So the first one is called the certainty equivalent. The certainty equivalent of a lottery is the amount of money, for sure, that makes the individual indifferent to the lottery. So if he's indifferent, whether he gets the money for sure or whether he plays the lottery is the same to him. We saw that if an agent is risk averse, then the average gain gives the agent a higher utility than the expected utility of the gamble. So if the agent is risk averse, we had a bigger with the expected gain. To get an equal, then, we would need the certainty equivalent to be lower than the expected gain. Otherwise, we would not get an equal. So if you're risk averse, the certainty equivalent will be lower than the expected gain. The idea is that you don't need as much money as the expected gain, for sure, to be indifferent between the gamble and taking the money and walk away. However, if you're risk neutral, we saw that the utility of the expected gain is equal to the expected utility. So this equality is exactly the same, and so the certainty equivalent in this case is equal to the average gain of the lottery. Now, the risk premium associated with lottery L is the difference between the certainty equivalent and the expected value of the lottery. So you take the difference and you get your risk premium P. So U of expectation of L minus P, which is the certainty equivalent, equals the expected value of the expected utility of the gamble. You can interpret the risk premium as the price you're willing to pay to be indifferent between no gamble and walking away with expected gain and taking the gamble. Now again, if you are risk averse, because the expected gain is bigger than the certainty equivalent from the previous slide, then the risk premium is bigger. That means that if you're risk averse, you are willing to pay a positive price to leave the gamble, to not play the gamble. And if you're risk neutral, because these two are equal, then the risk premium is zero. You don't need to pay a price or anything to be indifferent between no gamble and gamble. Let's look at the previous graph, and now let's look at what the certainty equivalent is going to be and what the risk premium is going to be. So we started here, but then we said that the certainty equivalent is defined as the utility that makes the agent indifferent between getting the certainty equivalent and playing the gamble. If the agent plays the gamble, his expected utility is right here. Expectation of U of L. So the certainty equivalent is going to be the amount X that you align with the graph, because it's U first, so that this point is aligned with the expected utility. You can see that both of these points are vertically on the same level. So the agent is indifferent between playing the gamble and get an expected utility, or get an amount of money equal to CE for sure and not play the gamble. Now, the risk premium is the difference between E of L and CE. So it's going to be this distance. Note that if the red curve, the utility function, was instead linear, then it will fall on the same line as the blue line, and there would be no risk premium. Any questions so far? Okay, let's take a 10-minute break. It's 1:12 right now. Let's start at 1:22 to talk about the third part of the lecture, which is insurance. Make sure in those 10 minutes you go over the slides to make sure you understand what's going on, because you're going to need this to follow the last part. Okay, we are back. So, now that we have defined what preferences over risky outcomes are, we are going to see how we are going to see how we model the way agents choose the amount of insurance they want to receive in case of a bad event. First of all, why is insurance popular? Well, because life is both uncertain and risky. Gains and losses can happen randomly. The principle of insurance is as follows. You pay an amount for certain, which we call the insurance premium. You pay this at the beginning of the year, for instance, to a firm, the insurance company, and the firm will insure you against bad events. So, if nothing happens, the only money paid is going to be the premium. You pay the premium at the beginning of the year, and you do not have to meet the insurance company the whole year. You do not have to file a claim, nothing like that. If a bad event leading to a loss happens, the firm pays you back either some of the loss or all of the loss. That depends on the contract. Couple of examples that probably you are aware of. Car insurance, house insurance against accidents, against car crashes, against fires, against earthquakes, against floods, for houses, this happens a lot. Health insurance against medical expenses. If because of unfortunate events you have to go to the hospital, emergency, get some medication, get some appointment with a specialized doctor, you might want to get an insurance so that the insurance pays you back some of the cost or maybe all of it. Employment insurance is also an example to insure a worker against unemployment. So once a worker finds himself without any job, if he worked for sufficiently long time before, he will be eligible for employment insurance, which means he is going to receive a certain amount of money. In general, it's a percentage of your previous wage for a certain amount of time. The point of employment insurance is to give enough time for somebody to find the best fit for his preferences and his skills. If you just lost your job and you have to pay if you have to pay rent and so on, you might just look for a job right away just to be able to pay rent. So you might just the day after go to McDonald's, go to Starbucks and say, okay, I need a job right now. I need to get paid to pay for rent. With employment insurance, you might get a couple months, which gives you time to upload or update your resume, make some job applications, interviews, and so on and so forth. So, let's look at the demand for insurance. Imagine that our agent faces two sorts of events: the good state event and the bad state event. In the good state, his income is going to be equal to Y dollars. This good state happens with a probability alpha. In the bad state, he's going to suffer a loss, L, and his income is going to be Y minus L. L could be, for instance, paying for car repair, or paying for the damage that occurred to your house, or paid for unexpected medical expenses, and so on. The bad state happens with probability 1 minus alpha. Now, insurance company here is going to propose a basic contract. The coverage is going to be called Q. The coverage represents the amount of money that the insurance is going to cover or pay you back in the case of a loss. And the premium that you're going to have to pay for Q dollars is going to be equal to pi dollars per dollar of coverage. So for each dollar that you want the company to give you back in the case of a bad event, you will have to pay an amount pi at the beginning of the year. So every time you deal with risk, expected utility, and so on, list all the outcomes and all the probabilities. So the income of the agent in the good state, that I'm going to label YG, G for good, is going to be the total income Y minus what the agent has to pay to the insurance company. Remember that the amount paid to the insurance company is fixed and certain. You pay that at the beginning of the year, whether something good or bad happens. So if nothing bad happens, your money is going to be Y minus the amount you paid to the insurance company. And the premium is equal to pi dollars per dollar of coverage. So if you get covered Q dollars, you will have to pay the insurance company pi times Q. In the bad state, it's a bit more complicated. In the bad state, the income of the consumer is going to be Y minus L, but the insurance company pays back Q dollars, hence plus Q, but the premium to the insurance company was paid anyway at the beginning of the year. So you see, I am listing all the possible things that are paid to the consumer or by the consumer in each possible state. Make sure you list that and make sure you don't miss anything that could cost you a lot of marks in exams. So the agent now has to figure out how much coverage he wants to get from the insurance company. Because on one hand, it is nice to get all the money back if an accident happens. But on the other hand, you have to pay pi dollars per dollar of coverage at the beginning of the year. So there is a cost and there is a benefit. So there is a trade-off. Our consumer is going to maximize his expected utility. Remember, he is at the beginning of the year. He is going to the insurance company and he's about to ask for a certain amount of coverage, Q. We want to know how much Q is going to ask for. So he's going to maximize his expected utility. With probability alpha, his money will be equal to Y minus pi Q, the good state money. So with probability alpha, his utility will be Y minus pi Q. Now, with the other probability, 1 minus alpha, well, bad stuff happens. So the income will be YB, Y minus L plus Q minus pi Q. And the utility will then be U of Y minus L plus Q minus pi Q. And we want to know what Q is going to be. The rest will be given to you. Y will be given to you, the loss will be given to you, the probability of accidents will be given to you, and so on. So let's take the first order condition. We take the derivative of the expected utility with respect to Q. At the optimal level Q star, this derivative will be equal to 0. That's the definition of first order condition. Now, let's get into the math. I strongly recommend you to do this at home to make sure you're not missing any piece. Because we're dealing with letters here and not numbers, things can get or can seem more complicated. They're not more difficult, they are more complicated. Big difference. So, if I take the derivative of the first term with respect to Q, I get alpha times U prime of what's inside times the derivative of what's inside. The derivative of what's inside with respect to Q is equal to minus pi. So my first term will be alpha times U prime times minus pi. Now, let's take the derivative of the second term. it's going to be 1 minus alpha times u prime of what's inside and times the derivative of what's inside. Q shows up at two different places, here and here. The derivative of what's inside with respect to Q will be 1 minus pi. And that's how I end up here with 1 minus pi. Oops, I was in the way. 1 minus alpha times u prime of what's inside times the derivative of what's inside. Now we are done and we make this derivative equal to 0. Remember, what we want to do is find q star. It's inside u prime, so of course right now I cannot solve it because I do not know what u is. If I give you a utility function, then you will be able to find it. Now, I'm going to rearrange some terms. You can see here I have minus pi. So I can take this whole term and put it to the other side to now turn this minus into a plus. And that's what I did in the second line. This left-hand side here corresponds to the second term here. And the right-hand side is the first term. Now, I just do this to show you some intuition. After doing this, you can keep the marginal utilities on the same side by taking the ratio. For instance, you take this utility, this marginal utility, and you divide it by this one. And on the other side, I'm going to put all the alphas and the pi's, and I end up with this condition. Now, a ratio of marginal utilities. That should ring a bell. Where have we seen this before? Or where have you seen this before? ECON 201. Remember that we have a ratio of marginal utilities when we compute the marginal rate of substitution. So, here we have the marginal utility in the good state divided by the marginal utility in the bad state. So this can be taken as a marginal rate of substitution from good state to bad state. If you increase the income in the bad state by $1, this is by how much your utility is going to, your marginal utility is going to decrease. Oh, how can I say this? This number here is by how much you need to increase your income in the bad state when you increase the income in the good state and stay indifferent between the two states. Anyway, the reason why I show this marginal rate of substitution is because we're going to show it on an indifference curve. Note that here we have a ratio of probabilities, 1 minus alpha over alpha, and we have a ratio of relative prices. Pi is remember, pi is the premium per dollar of coverage. This is the amount you have to pay per dollar that you want to receive if something bad happens. Now, at this stage, alpha is given to you, y is given to you, L is given to you. This is how much money you have, how much money you might lose, and with what probability events can happen. But we don't know pi. Pi is decided by the firm. Pi is how much the firm is going to get for each dollar that you want to be covered. To make things simple, we are going to assume that the insurance market is competitive. What does that mean? It means that profits, expected profits, will be equal to 0. So the expected profit for the insurance company is going to be the following. With probability alpha, nothing happens. So the insurance company does not need to give any money to the consumer, but it receives the premium. The total premium will be pi times Q. With probability 1 minus alpha, an accident happens and the insurance company still receives the premium, but now has to give Q dollars back to the consumer to compensate him for the damage or the accident. Now it turns out that if you make this thing equal to 0, because the insurance market is competitive, then you obtain that pi will be equal to 1 minus alpha. And I strongly suggest you to try this math at home. When pi, which is the premium per dollar of coverage, is equal to the probability of a bad event, we say that insurance is actuarially fair. What you pay per dollar of coverage corresponds to the probability of a bad event happening. Note that 1 minus alpha is between 0 and 1, so pi is between 0 and 1. So if you want the insurance company to give you $1 back when bad things happen, you need to pay the insurance company 50 cents at the beginning of the year. Now, if you apply this result to the previous math, to the previous formula here, well, we said that 1 minus alpha was equal to pi. So these two numbers are going to cancel out. And that also means that 1 minus pi is equal to alpha. So this number is also going to cancel. We end up with the right-hand side being equal to 1. If they were equal to 1, if the right-hand side is equal to 1, it means that this ratio is equal to 1, which means that u prime in the good state is equal to u prime in the bad state. This is what we obtain. Now, having a concave utility function is going to imply that Q star is equal to big L. You can actually do the math. It means that what's inside here is equal to what's inside here. And you obtain that the optimal amount the consumer wants to be insured is equal to the full amount of the loss he is risking. So this is what we call full insurance. If you get into an accident and the damages are worth $5,000, the insurance company pays you back $5,000. And this leads to a very important result. If insurance contracts are actuarially fair, so we have this first condition, risk-averse individuals will fully insure themselves against all income risk. If they can, of course. Any questions? So you need two ingredients for full insurance. You need a risk-averse agent and you need actuarially fair rates. If you don't have one or the other, then insurance will be partial. You won't want to be covered your full amount of the loss, but you will want to be covered maybe 50% of it, or maybe 70% of it, or maybe 30% of it. let's look at how it illustrates graphically. So instead of representing x1 and x2, in this graph, I'm going to represent income in the good state and income in the bad state. Okay? Now, let's start with point A. Point A corresponds to the income without insurance. If you don't get any insurance and nothing happens, your income is equal to Y. If, however, bad things happen, an accident, but you're not insured, your income will be Y minus big L. Now, this red curve is the indifference curve, along which any pair of incomes would make the individual indifferent. It would give the individual the same expected utility. So remember here, this is an indifference curve for expected utility, not just for utility. And point A corresponds to the point where the consumer is at before buying any insurance. And so his expected utility corresponds to this indifference curve, whatever level that is. Now let's include insurance in the mix, and let's see if the consumer prefers insurance or not, or what kind of insurance he prefers. Now, we saw that our consumer, if he is risk averse and prices are actually fair, then he's going to go for full insurance. Full insurance, you can look at the previous equation. Full insurance means that this amount, which is the income in the bad state, is equal to this amount, the income in the good state. So, if they are equal, it means that under full insurance, whether you're in the bad state or in the good state, your income is the same. Call it Y star. And this is where we are on the indifference curve, on the 45-degree line. That corresponds to the case where YG, the good state income, is equal to YB, the bad state income. And that's point B. The slope of this line here is minus alpha over 1 minus alpha. It is the relative likelihood of a good event as opposed to a bad event. If alpha is equal to 0.5, 50%, then this is equal to 1. That would mean that each event is equally likely. So this blue line corresponds to the budget line if the company offers coverage Q at a price pi equal to 1 minus alpha, if the rates are actuarially fair. So we saw that when they are fair, the consumer wants to fully insure himself against risk, and this is why he ends up on point B. If he gets insurance, he's going to choose point B, as opposed to this point, or this point, or this point, or this point, and so on. Now, at that point B, what is the corresponding indifference curve? Well, it's going to be this red indifference curve. And you can see that it is higher than the original indifference curve, which happened under no insurance. And you can see that this indifference curve is the highest possible indifference curve that touches the budget set. The budget set is this blue line, is given by this blue line and any point below. Any point here is an income that the individual can get to in good versus bad state. So, this graph shows that our consumer, if he is risk averse and rates are fair, is going to go to full insurance. And full insurance will yield a higher expected utility than no insurance. Okay? Any questions about this graph? It's a very important graph, but there are a lot of things going on. So take it step by step. We started with the baseline no insurance case, point A. Then we went to, if we have insurance, what are we doing? We are going to point B, and at point B, we have a higher indifference curve. Any questions? Okay, so let me summarize everything we saw today. There we go. So, expected utility is a way to measure utility over an outcome that might not happen with a probability of 100%. We don't really care about the expected gain, we care about the expected utility over the gain. Why are these different? Because $100 is not worth the same to me than it is to you. Think about Bill Gates or Jeff Bezos. For them, $100 is nothing. They don't even think about it. It's like that's what they would tip the waiter at a restaurant. For me, $100 will give me a lot of utility because I'm cheap. So, an expectation is an average. You might have seen this term in courses like ECON 333 or Buex 333, which are statistics courses. An expectation for a random variable is simply the average value that this random variable takes. So the expected utility function is going to assign a utility value to each possible outcome. In order to look at whether one lottery is better than another, then we can just compare the expected utilities to figure out which gamble one consumer prefers to play. I gave two examples, two lotteries with a utility function, and that's something I strongly recommend you to practice at home. Then we went into what does it mean to be risk averse and how do we compare two individuals who are both risk averse. First of all, we need to define what it means to be risk averse. This is why we compared, well, the expected utility of playing the gamble, and we linked that with the utility, so the certain utility from gaining the average amount of the lottery or of the gamble. We saw that risk aversion is defined as U of expectation of L bigger than expectation of U of L. So the agent prefers to get the average value of the lottery for sure over playing the lottery itself. We saw on a graph what it looks like. Expected utility will be on the blue line, here in the middle because it's half and half, but not necessarily in the middle, but it's on the blue line. Whereas the utility of the expected gain will be on the red curve because U is first. When U is first, you are on the utility function. And now you can see that vertically speaking, the red term is higher than the blue term. I also mentioned that we can see that anytime a function is concave, the straight line linking 2 points from the graph, the straight line will always be under the corresponding points on the graph. So as long as my agent has a concave utility function, he is going to be risk averse. And that's what led us to this theorem. So we defined the general inequalities here. Then we reversed those inequalities to define risk neutrality and to define risk loving behavior, which is just the opposite. It also means that if the agent is risk averse, his utility function is strictly concave. If he is risk neutral, his utility function is linear. And if he is risk loving, his utility function is convex. So as soon as you see utility function and you see risky outcomes, you should immediately look at the utility function and wonder, is our consumer risk averse, risk neutral, or risk loving? Just by looking at the shape or looking at the second derivative, you can tell whether a consumer is one or the other. We then came up with a measure of how risk averse one individual is compared to another individual. Two individuals could be risk averse, but the coefficient of risk aversion is going to tell us which one is more risk averse. The relative risk aversion is another measure that corresponds to the elasticity of the marginal utility with respect to money. So it's a percentage. It measures the percentage change in marginal utility when money increases by 1%. I took an example that, again, I strongly suggest you to work on. You will be asked to do similar computations, so the more practice you get, the better. I went over the case of a square root utility function that has a decreasing absolute risk aversion coefficient, so it's a Dara utility function, and at the same time it has a constant relative risk aversion, because this x here cancels with that x there. And so this utility function is also a CRRA utility function. And I strongly suggest you to try with those ones, x minus 1/2 x squared and minus 1 over x at home. You can come to office hours or ask by email if your results are correct. I'll be happy to double check them. Then I went on to defining the certainty equivalent, which is the amount of money for sure that makes a consumer indifferent between not playing the gamble and playing the gamble. So once you compute this, you just have to find this number that makes this utility equal to this number. So it's not very complicated to find. If you know the agent is risk averse, you can double check your result by checking that indeed the certainty equivalent is lower than the expected gain of the lottery. Always a good one to, always a good property to use to double check your results. I also defined the risk premium, which is the difference between the certainty equivalent and the expected value of the lottery. Again, once you have the certainty equivalent, you can find the risk premium, or you can find the risk premium first, since you can find E of L, and you can also find the expected utility of the lottery. I showed how they look like on a graph. CE is going to be horizontally aligned. Well, no, vertically aligned. Horizontally aligned, sorry, with the expected utility, because vertically speaking, they are at the same level. And the risk premium will be the difference between the expected gain and the certainty equivalent. Note that what's on the x-axis is money, so expectation of L is money. What's on the y-axis is utility or expected utility, which is doesn't really have a unit. I guess you can express that in terms of dollars, but just to make a distinction that on the y-axis you only have use. And on the x-axis you have no use, just money. Finally, I talked about insurance, and I looked at how a consumer will decide how much insurance to get, depending on his preferences, and of course, depending on how much he has to pay for each dollar of coverage. Again, I strongly suggest you to do these computations at home. Take this first order condition. Make sure you can find everything. We found that if the agent is risk averse and if prices are actuarially fair, with those two conditions, then full insurance is what is optimal. Full insurance is what maximizes the expected utility of our consumer. And on a graph, we find that once we show the budget constraint under insurance, this blue line, the highest possible indifference curve is going to touch the budget line at point B. And at point B, the x coordinate here is equal to the y coordinate. That corresponds to full insurance. That means that whether something good happens or something bad happens, the consumer will always have the same amount of money in his pocket. In one case, he pays the insurance company and that's it. In the other case, he pays the insurance company, then a loss happens, but he gets the full amount of the loss paid back to him. The end result will be the same. That's what full insurance is about. That's it for this lecture on risk. Have a good rest of your week and see you in the next one. Bye.